So is the screen visible?
Yes, sir.
Okay. All right. Thank you. So today we'll define what I'm going to call the Bernoulli function, and a term which is referred to by hydraulic engineers as head. So the Bernoulli function is defined by equation 1, which is written on the screen. So I'm using the symbol capital B for Bernoulli. So it is the sum of three terms. The first term is the fluid pressure. So this is the absolute static pressure. So the units of this will be pascals in SI units or Newton per meter square. The second term represents the potential energy of the fluid per unit volume. And of course, this we are going to apply to the flow of water. So we can assume the density to be constant. So I've emphasized here rho is the constant density of the fluid. So for variable density flows, we have to make some modifications, which we don't need in this course. And g, this vector in bold, is the gravitational acceleration. Again, we are assuming it to be constant. Now you know that the value of g varies if you go upwards towards outer space, but we are not dealing with flows where the length scales are that large. Okay, so the variation of g close to the surface of the Earth can be neglected, and we will assume that g is a constant gravitational acceleration. So I've used the symbol r to denote the position vector of a point. So any letter which is appearing in boldface is a vector quantity. So r is xex plus yey plus zez, where ex, ey, and ez are the unit vectors in the x, y, and z directions. And I've used x, y, z to denote the Cartesian coordinates of a point. Well, I just noticed a typo. These should have been coordinates. So these things I'll iron out before I send the material to you. Now, in your mechanics courses, you might have used the symbols I, J, and K for the unit vectors in the x, y, and z directions. Okay. We will also be using cylindrical coordinates, where we'll use unit vectors ER, EPhi, and EZ. Okay. So I thought that in keeping with that notation, if I write EX, E subscript X, E subscript Y, and E subscript Z, that will be better. So E subscript X is the unit vector in the X direction. E subscript Y is the unit vector in the Y direction. And E subscript Z is the unit vector in the Z direction. Now the third term here in equation 1, half rho V dot V, where V is the fluid velocity. So this represents the kinetic energy per unit volume. So V dot V will be the magnitude of V whole square. Okay. Now you know that half mv square is kinetic energy, and rho, the density, is mass per unit volume. So the units of this term is energy per unit volume. So this will be joules per meter cube. Okay. So this last term is the kinetic energy of the fluid per unit volume. And the middle term here is the potential energy per unit volume. Now potential energy would be minus mg dot r in vector notation. And rho is mass per unit volume. So this is potential energy, gravitational potential energy per unit volume. So units will be joule per meter cube. And P, the pressure, as units Newton per meter square. So if you multiply Newton per meter square, if you put a meter in the numerator and the meter in the denominator, you will see that Newton per meter square and joule per meter cube have the same units. Okay. So this is a Bernoulli function that we are going to use. So I've introduced my notation. I'm going to use capital B for the Bernoulli function. Now you will note that this middle term actually is a group of three terms. it will be G dot R will be Gxx plus Gyy plus Gzz in general for an arbitrary coordinate system. And similarly, V dot V will be a sum of three terms, that is square of the x velocity plus square of the y velocity plus square of the z velocity.
Sir,
Yeah,
I have a doubt here.
yeah, yeah,
So the situations that we are dealing,
yeah.
in that, do we assume that Bernoulli's theorem applies?
We'll be using Bernoulli's equation with a head loss term, which will account for frictional effects.
Okay. Yes, sir.
Okay, but to begin with, there are places where we are going to assume that the fluid is an ideal fluid. Okay, so
Yes, sir.
Bernoulli's equation may be valid, but we must be careful in using it.
Yes,
For
sir.
instance, you must know what are the conditions under which this will be valid. So right now I'm just defining a function which I'm calling Bernoulli function. Okay,
Yes, sir.
so these are the terms which appear in Bernoulli's equation. So Bernoulli's equation tells you that the value of the Bernoulli function that I have defined above is a constant, but under what conditions? Well, I have listed all the conditions over here. So let us look at the second one first. The flow has to be steady. Now you know what that means. It means that while flow quantities can vary with space at a given spatial location, there will be no variation with time. Okay. And we are going to assume the fluid is an inviscid fluid. Or I'm calling it inviscid flow because actually there is no fluid which is truly inviscid. Okay. But even in a viscous flow or viscous fluid, there could be regions of the flow where the strain rates are small and viscous forces are negligible. Okay. Then if you assume that the fluid is an inviscid fluid, the prediction will be a good prediction. So I'm deliberately using the term inviscid flow rather than inviscid fluid. So you can have inviscid and approximate inviscid flow of a viscous fluid. That's what I'm trying to say. Okay. Now, as I said before, I'm assuming that the density is constant. You can have forms of Bernoulli equation where density is not constant, but that form will be more complicated. And I'm assuming that it's a conservative vibration. Yeah.
So can you just repeat that inviscid flow and with a viscous fluid?
Okay. See, if you consider a fluid particle, there will be a viscous force on the particle when the fluid is viscous and the fluid is deforming. For instance, you look at Newton's law of viscosity. You say that tau xy is mu du dy for a one-dimensional situation. Or not one-dimensional situation, a situation where there is only one component of velocity in the x direction which varies with y. But suppose the velocity distribution is uniform. Okay, in that case, what is du dy? The value is 0. So what is the shear stress due to viscous effects? That is mu times 0, which is 0. Okay. So when the velocity distribution is uniform everywhere, the fluid may be a viscous fluid, but there will be no viscous force on a particle. Okay. So it behaves as if it's an inviscid fluid. Have you followed what I'm trying to say?
Sir.
So there could be other cases where, so the viscous force, if you look at Stokes' law of viscosity, the viscous terms have the viscosity multiplied by a strain rate term. So sometimes you could have a flow field where the strain rate is small or even 0. Okay. In that case, the viscous forces can be neglected.
Sir, but in that case, the no-slip condition would be invalid, right?
Pardon?
In that condition, when strain rate is 0, in that condition, the no-slip condition will become invalid because at the junction, at the interface, there will always be a gradient, isn't it?
Right. So there'll be if the Reynolds number is high, there'll be a boundary layer which will be thin. But outside the boundary layer, it may behave like an inviscid fluid. Okay. So what will happen is when you have high-speed flow past a solid plate, let us say, okay, viscous effects are confined to a thin region close to the surface, which is called the boundary layer. So within the boundary layer, the velocity in the tangential direction tangential to the plate will go from 0 to some value. Okay, it is 0 because the viscous fluid will stick to the surface. That is what you call the no-slip condition. Okay. But if you look at the region outside the boundary layer, it's a viscous fluid, but the viscous forces are negligible, almost zero. So there you can make an approximation assuming the flow to be inviscid. Of course, in this course, we are going to assume that it is inviscid throughout, so we'll not enforce the no-slip condition. Okay. So I'll come to that later. Okay. So what I'm trying to say is you can apply Bernoulli's equation when the viscous forces are negligible on a particle. Okay. But even if the last four conditions are valid, the value of the Bernoulli function is a constant only if you take 2 points on the same streamline. So I made another comment here. The numerical value of the Bernoulli function V varies from one streamline to another streamline in steady inviscid flow of a constant density fluid in a conservative gravitational force field, unless the flow is also irrotational. Okay. So if the flow is irrotational, then Bernoulli's equation can be applied between any 2 points in the flow field, provided the last four conditions is also satisfied. Okay. But if the flow is rotational but inviscid, you can have inviscid rotational flows where the vorticity is non-zero, then you cannot apply Bernoulli's equation between any 2 points. That is, the sum of pressure, potential energy and kinetic energy will not have the same value at all points. But if you take points on the same streamline, then they will have the same value, provided the other four conditions are satisfied. So this is something you have studied in your second year course. Now in this course, we'll be applying Bernoulli's equation in a frame of reference which is translating. Okay. So I'll come to that slowly, and there I will again quickly derive Bernoulli's equation. Bernoulli's equation can be derived in many ways. Okay. So I'll give you a brief derivation which will also be valid for the case when the frame of reference is stationary. But if I start deriving Bernoulli's equation in a frame of reference which is stationary, you will get bored because you have already seen something similar before. So today I'm just giving you the result which you already know, but I want to emphasize that these 5 conditions have to be satisfied. Now I have not yet said what is a conservative gravitational field. Okay, so I'll come to that. Perhaps you know it already. Okay, now but anyway, since I've talked about irrotationality, whether we use it or not in this course, I thought let me refresh your memory. The flow is irrotational if the vorticity is 0. So vorticity is defined as the curl of the velocity. Now the curl of the velocity is a vector quantity. So I've written 0 here in bold. So this is the 0 vector or the null vector. So that means all the 3 components of vorticity are 0. If that condition is satisfied, then you say the flow is irrotational. Now, the force field, body force field, such as a gravitational field, is said to be conservative if the curl of this force field, in this case G, is the 0 vector. When this is satisfied, the work done by the gravity force on a particle is independent of path. It just depends on the position. So in our case, we are assuming G to be a constant vector. And as you might have studied in a second year course, you can write G as grad of G dot R. Now you know curl of grad is always 0. So if G can be written as grad of G dot R, then curl of G will be curl of grad G dot R, which is 0 vector. So when the gravitational acceleration is constant, we know the gravitational force field is conservative. So if we come back and look at these conditions, the last condition will always be satisfied for the cases which we are going to consider in this course, because we are going to assume that the gravitational acceleration, the vector, is a constant vector. And we are going to deal with flow of water, which is a liquid. We can neglect density changes. So the second last condition, the constant density fluid, is also going to be satisfied. Okay. Now this inviscid flow may or may not be satisfied. So first we'll make a prediction assuming it to be inviscid, and then we'll account for the viscous losses through a head loss term. So we'll get a practical engineering prediction using without solving the Navier-Stokes equations. Now this point about whether it's steady or not actually may depend on the frame of reference that you're going to choose in the analysis. Okay. So if you recall, in the previous class, I'd shown you a figure of a bucket of the Pelton wheel which was translating, and I had used two reference frames. One was a stationary frame, the other was attached to the moving bucket. Okay. And in most books, they'll make a statement that the flow is steady in the moving frame without explaining exactly what it means and how that differs from the statement that the flow is steady in a stationary frame of reference. So I'll talk about those in more detail, but first let me complete this and introduce my notation. Okay. The first restriction on Bernoulli's equation, that is actually the most important one, that the value of the Bernoulli function is a constant only along points which are on the same streamline. So if you move from one streamline to the next streamline, the value of the Bernoulli constant may change. So that is something you have to keep in mind. Okay, now let us look at a special case. Suppose you have a liquid, a constant density fluid, which is at rest in a gravitational force field. In that case, the velocity is 0. So if you go back and look at the Bernoulli function here, if the velocity is 0, its magnitude is 0, so the last term will be 0. So then the Bernoulli function will be simply p minus rho g dot r. Okay, and this quantity will be a constant in a fluid which is at rest, that is the static fluid. So this quantity p minus rho g dot r, some people call it a modified pressure, and some authors refer to it as piezometric pressure. So this small p we'll call static pressure, and this quantity p minus rho g dot r we'll call piezometric pressure. Later on I'll talk about stagnation pressure. Now we come to the quantity which we call head. So head is a term which is used by hydraulic engineers. So this is simply the Bernoulli function which I have defined before divided by rho times g, where rho is the constant density of the liquid. Okay, and this g, scalar g here, is the absolute value of g, which is the magnitude of the acceleration due to gravity, and we'll assume that it has a value of 9.81 meter per second square. Of course, sometimes for simplicity we may assume it to be 10 meters per second square, because 10 is a round number. Okay, so if I go back to the definition of the Bernoulli function and divide the left hand side by rho g, then each term on the right hand side will be divided by rho g, and then each term on the right hand side will have units of meters if you use SI units. So hydraulic engineers like to deal with units of meters. So I'm writing it in this form: P by rho h, capital H is the symbol which I'm using for head, or you can call it total head. It is P upon rho g minus g dot r by the magnitude of the g plus v dot v by 2g. So this half is there because it is a kinetic energy term. Now I can write the gravitational acceleration as the scalar g times the unit vector in the direction of the gravity. So this symbol g with the hat indicates that it is a unit vector. So the definition of g is g hat is g divided by its magnitude. So this is the unit vector which will be pointing vertically downwards in the direction of the vector g. So if I use this equation 4 and substitute over here and write in the numerator the vector g as the magnitude g into the unit vector g hat, then the g in the numerator and denominator will cancel out. Okay, and I can write this as h as pa by rho g plus v square by 2g minus g hat dot r. Now here I've used a different notation. I've used capital V to denote the magnitude of the fluid velocity. So this capital V is the absolute value of the vector v, which you can think of as square root of v dot v. So capital V square is v dot v. And v dot v, if you write in Cartesian coordinates, will be vx squared plus vy squared plus vz squared. Now these relations that I've written, I've numbered these equations because I'll be sending this to you and you can look at it later on. Okay. These are invariant under coordinate transformation and they therefore hold for any coordinate system. Now, if you look at the first term here, P upon rho g, this is called pressure head. So to be more precise, the quotient P upon rho g is termed the pressure head corresponding to small p. So this is the pressure head corresponding to the static pressure P. And the quantity magnitude of V square, capital V square by 2g, or equivalently V dot V by 2g. This is sometimes called velocity head. So this is a measure of the kinetic energy of the fluid, but in units of meters. And the other term minus g hat dot r, or minus g dot r by magnitude of g, this is called elevation head. So this is proportional to the gravitational potential energy of the fluid. So the total head I can write as the sum of the pressure head, velocity head, and the elevation head. Now, the term P minus rho g dot r by rho g is sometimes called piezometric head. So if I go back over here to this equation, the first term and the second term, if I look at it together, the sum of this I can call the piezometric head. So the total head I can also write as the sum of the piezometric head and the velocity head. So you can view it in two ways. The total head is the sum of three heads: the pressure head, the velocity head, and the elevation head. Or you can think of it in two ways. Total head is the sum of the piezometric head and the velocity head, because the piezometric head itself is the sum of the pressure head and the elevation head. And as I have mentioned before, and it's obvious to you, all these quantities, pressure head, velocity head, elevation head, piezometric head, and total head, they have the dimensions of length. So the SI units will be meters. And hydraulic engineers prefer to deal with quantities which are the units of meters. Now consider a coordinate system where the z-axis is vertical and the unit vector Ez is in the direction of z, which is pointing upwards. Then I can write the gravity vector as minus of g Ez, where small g is the scalar g is the magnitude of the gravitational acceleration, and Ez is a vector pointing upwards, unit vector. The minus sign is there because g points downwards. In that notation, I can write the head as P by rho g plus v square by 2g plus z. So this is the form that you might have seen in your second year course, but you have to keep in mind that this is valid only when you have chosen a coordinate system such that two conditions are satisfied. The z-axis is vertical and the z-coordinate increases as one goes upwards. Now I could also take a z-axis which is vertical and the z-coordinate increases as one goes downwards. That is, I can take a coordinate system such that Ez points downwards. Then you have to modify equation 7 and write this as minus z. Okay. Now you may have while solving a problem, you may choose a coordinate system where the y-axis is vertical. Then instead of z, you have to substitute y. Okay. So when you solve problems, be sure to show, and you are dealing with vector quantities, don't forget to show the coordinate system and the origin. Now that is the reason why I wrote the Bernoulli head in this form, g dot r by g. So in this form, I can take any coordinate system. It could be an inclined coordinate system where none of the coordinate axis is vertical. Okay. So if you are looking at flow along an inclined pipe, you may take the z-axis to be the axis of the pipe. Okay. So that is a source of confusion for students. They may confuse that z-axis for the inclined pipe with the z in equation number 7. Okay. So you have already had a course on fluid mechanics. And right now you're a fourth year student. I view this as a second level course where you need to be precise. So that is why I've used this kind of notation. And also, if I keep using the same notation that you have seen in your second year, you will get bored. Okay, so you are seeing the same thing in a different way. All right. So I want to emphasize that equation 7, the definition of head, while this might be useful when solving problems, this is not valid unless the z-axis is valid. And also, I forgot to write over here, the Ez must be pointing upwards. Whereas the vector relation 5, okay, this one is valid for any coordinate system. Now, if you consider a steady flow of an ideal fluid, then the total head will be constant along a streamline. But if the flow is rotational, the value of this constant will vary from streamline to streamline. Now, you know what's an ideal fluid. You must have studied ideal fluid flow in your second year, but that was 2 years ago. Okay. So I've written here in brackets what it means. It's a fluid with constant density and zero viscosity. Now let me ask you a question. Is an ideal gas an ideal fluid?
No, sir.
Why?
Sir, the density is not constant in a gas.
Exactly, the density is not constant. So next semester you will face a comprehensive viva. Okay. So in a comprehensive viva, these are the kind of questions that one might ask. Okay. So I thought that I should emphasize it. An ideal gas is not an ideal fluid. So an ideal gas will satisfy the relation P equal to rho RT. So the density will depend on pressure as well as temperature. Okay. Now let us review head loss in viscous flow through a duct. So we'll consider steady viscous flow now, and we'll assume the density to be constant, so it could be flow of water or any other liquid. So consider 2 points on a streamline. I'll label those points 1 and 2. Now let the downstream point be 2 and the upstream point be 1. Okay. Now had the fluid been inviscid, then H1 the head at 1 and the H2 the head at 2 would have been the same. But if it's a viscous flow, it may not be the same. So this difference, H1 minus H2, is referred to as the head loss between points 1 and 2. So I'm putting this subscript LOSS for loss. Okay. So in most cases, if 1 is the upstream point and 2 is the downstream point, H1 will be larger than H2, so there's a loss of head. So I'll discuss this in more detail later on. But first of all, let me define what I mean by head loss. So I can write simply H subscript loss, or to be more precise, I can put a parenthesis, put H loss in the brackets, and here outside the brackets, I can put a subscript 1-2. That means the head loss between 1 and 2. So that is simply H1 minus H2. Now you could look at head loss in a compressible fluid, then I will say B1 by rho 1 G minus B2 by rho 2 G. But here actually we'll be dealing with a case where rho 1 equal to rho 2. Okay. So first I'm just writing it this way. So V I've written here in parenthesis the sum of 3 terms. And here it is the sum of the same 3 terms, but the subscripts are different. So here you have P1 rho 1, V1 and G dot R1. And in the second group of terms, you have P2 rho 2, V2 and R2. So the subscript in the first group of 3 terms is 1, and the subscript in the second group of 3 terms is 2. Okay. But here in this course, we'll be dealing with constant density flow. So I'll not put a subscript on rho. Okay. So if I go back over here, I can, if rho 1 equal to rho 2, I'll just simply call it rho and I can factor it out. So the head loss will be for a liquid simply the difference V1 minus V2 by rho g. So I'm writing the same equation again here, but I have not put any subscript on rho. This is subscript on P, this is subscript on the velocity. So this is the magnitude of the velocity, and there is a subscript on R, the position vector. And this, don't forget, this is the hat, that is the unit vector. Now if I want, I can group it separately, the difference of pressure, difference of kinetic energy, and the difference of potential energy. Now, this is a course where we will talk about turbo machines, and we'll be talking about energy being either added to a fluid or being extracted from a fluid. So it's convenient to talk about differences of pressures, differences of kinetic energy, and differences of heads. Right now, of course, I'm dealing with duct flows. Now, if I want, I can factor out the G. So I can write this 1 by G. Then I will have the delta P by rho, P1 minus P2 by rho. Then here I will have half V1 square minus V2 square. And this is, don't, you have to notice carefully, I have put a hat on top. So this G hat is the unit vector, which is G divided by G. So if I factor out the scalar G, then this is the gravitational acceleration, the vector denoting the gravitational acceleration. Whereas the previous term here, this was the unit vector in the direction of G. Now, this head loss actually represents the loss of available or useful mechanical energy. So the sum of pressure, kinetic energy, and potential energy you can view as mechanical energy. And mechanical energy can be easily converted to work. The second law of thermodynamics will not put any restriction on that conversion of work. So you have had a course on basic thermodynamics. You know that in a continuous system, heat cannot be completely converted to work in a cyclic process. A process has to be cyclic if you want to continuously extract work. Okay. So while in a non-cyclic process, you can convert all of heat to work. Okay. You cannot do it continuously. You have to use a cyclic process, and in a cyclic process, you cannot convert all of the heat to work. So if you look at the efficiency of a heat engine, it will never be 100%. And typically it is very small. Okay. But here, hydraulic turbines, you will see, will have very high efficiencies. So the viscous loss, you can view as a loss of available energy. So this loss is due to viscous effects. All right. Now, before I proceed further, then I have to review a bit of thermodynamics, and then I'll come back to this head. Okay. So what I'll do is I'll stop sharing this and I'll open another document. Okay, sorry, I got logged out accidentally. Okay. Okay, so let us look at some aspects of thermodynamics which are relevant to the study of fluid machines. Now in thermodynamics, you would have studied about closed system and open system. Now in fluid mechanics terminology, an open system is referred to as a control volume. So authors of books on thermodynamics will talk about open systems, and authors of books on fluid mechanics will refer to the open system as a control volume. Okay. So I have listed some of the characteristics of a control volume. Fluid particles will enter through some parts of the control surface and leave through some parts of the control surface. So by control surface, I mean the boundary of the control volume. And since fluid particles enter and leave, mass transfer will occur across the boundaries. Of course, there may be some parts of the control surface where fluid neither enters nor leaves. Okay, so there could be solid impermeable surfaces, and there could be inlets and outlets. So through the inlets, fluid particles will enter, and through the outlet, fluid particles will leave. So usually when you get a sketch of a control volume, you use dotted lines for the boundaries. So the space between the dotted lines is sort of indication that it is open to mass transfer. So when it's an open system, we mean open to mass transfer. So mass transfer can occur across the boundaries of the control volume or the control surface. Now suppose the flow is steady, then the mass of fluid inside the control volume will be a constant, which is independent of time. However, the identity of the matter inside the control volume will not be the same, because particles will enter and particles will leave. Now we are dealing with continuum mechanics, so we are not talking about molecules. Okay. Particles, as you know, in continuum mechanics are hypothetical quantities. You can view them as a collection of particles, a collection of molecules. Okay. So each point is a particle, and a fluid is comprised, will consist of an infinite number of particles. Okay. So the identity of the matter is fixed by the identity of the particles. Now, in the case of an open system or control volume, particles will enter and other particles will leave. So even if the mass of the fluid which is inside the control volume is independent of time, the identity of the matter will not be the same. Now, you can have stationary control volumes or moving control volumes. Now again, I spotted an error, typing error, I have written off instead of or. So I'll correct all this before I send it to you. So what I mean is the control volume may be stationary or moving, and sometimes it may deform also. Okay. But here we'll talk about, we'll use control volumes of fixed shape and size. So we'll be dealing with non-deforming control volumes. Now in the case of the analysis of the Pelton turbine, we'll have to use the moving control volume. Okay. So first anyway, let me talk about the control volume, which is not moving. Okay. So in many cases, you may have a control volume where there is one inlet and one outlet. By inlet, I mean a part of the control surface where fluid particles will enter the control volume. By outlet, I mean a part of the control surface through which fluid particles go out of the control volume. So you can refer to the outlet as an exit. Okay. So I'll use the term section 1 for the inlet and section 2 for the outlet. Now we'll consider a case where the flow is steady. And of course, right now I'm not introducing a moving coordinate system. So it's just a stationary coordinate system. And for simplicity, we'll assume that the flow streams are one-dimensional at points where mass crosses the control volume boundary. So if you look at the velocity profile at the inlet and outlet, actually it will not be one-dimensional, because velocity, if it's a viscous flow, will be zero at the solid wall. So if it's a pipe, okay. But then the analysis becomes too complicated. Okay. So we'll make predictions assuming that the distribution of the velocity is one-dimensional. So the flow, if you look at any point at the inlet, we'll assume that the velocity does not vary across. either the inlet or the outlet. So in other words, we are going to assume the velocity distribution to be uniform across the inlet and outlet. Now, when you make this one-dimensional approximation, the mass flow rate simply will be the product of density of the fluid times the magnitude of the velocity times the area. And of course, here we are assuming that the velocity is normal to the section. Okay. So I've used the subscript 1 for the quantities at section 1, which I'm calling the inlet, and the subscript 2 for the quantities at the outlet, which is section 2. So for the sake of completeness, although it's obvious to you, we have seen this before, I have defined what is V, A, and rho. So V, capital V, is the magnitude of the velocity vector. Okay. And here I am assuming that the section is normal to the direction of the flow. Okay. And capital A is the area, and rho is the density. And the subscripts 1 and 2 refer to sections 1 and quantities at section 1 and 2. Now, if we apply global conservation of mass and assume that there is only one inlet and one outlet, and the flow is one-dimensional at the inlet and outlet, then once steady state is reached, you will have m1 dot equal to md dot. That is, the rate of mass flow rate through the inlet will be equal to the rate of mass flow rate through the outlet. In that case, I'll simply call it m dot without any subscript 1 or 2. But if you have flow of a compressible fluid and it's unsteady, then mass might accumulate inside the control volume because the density can change. Density of the fluid inside the control volume can change. In that case, m2 dot may not be equal to m1 dot. But even if it's compressible, if steady state is reached, then the density at each and every point is not changing with time. So the mass of fluid inside the control volume remains same. In that case, the mass flow rate coming out of the exit will be equal to the mass flow rate entering through the inlet. Now, of course, here we'll deal with a situation where the density is constant. So if rho 1 and rho 2 are the same, I'll drop the subscript and simply call it rho. So in the case of a liquid, then I'll say m1 dot is rho times q. Now, sometimes we are going to use q for heat transfer. So I will put a subscript here, FLOW, to tell you this is the volume flow rate. So m1 dot will be rho times the volume flow rate, and the volume flow rate at section 1 will be the product of the velocity and the area. So velocity will be meter per second, area will be meter squared. So this will be meter cube per second, volume flow rate. All right. Now let us look at the global conservation of mass. So by global conservation, I mean the conservation principle applied to a large chunk of fluid. And by local conservation, we'll meet the same conservation law applied to a particle of infinitesimal volume. Anyway, in this course, we'll be dealing mainly with global conservations. So when the density of the fluid is a constant, even if the flow is unsteady, m1 dot will be equal to m2 dot. Can you explain why?
Sir, because the fluid is of constant density for a fixed control volume, the volume is fixed, so the mass inside should also be fixed as the density is fixed.
Right. Since the density is constant and the volume is also constant, the control volume is not deforming, the mass of fluid inside the control volume at any instant of time is the same. So we cannot pack more fluid into it, fluid or more mass into it. So since the density cannot change, the total mass of fluid, although the identity of the fluid is changing, the total mass of fluid inside the control volume is the same. So therefore, in kg per second, whatever mass enters through the inlet must go out through the outlet. And this also implies that the volume flow rate is the same. So it is also conservation of volume. Okay. So conservation of volume and conservation of mass will give you the same answer in this case. Because here the rho on the left hand side and the rho on the right hand side will cancel out. Okay, now we have to look at the global balance of total energy. which is the first law of thermodynamics. Now we have to apply it to an open system. Now in your course on thermodynamics, you must have come across this term steady flow energy equation. And you might have applied it usually to control volumes with one inlet and one outlet. So here I've just written it down. Now last year I had access to a blackboard, so I had actually derived it, but today I'm just writing it down over here. If there are queries, I'll answer later. So it is the mass flow rate m dot times the energy that is flowing into the control volume through the inlet, plus the rate at which energy enters as heat. So here this capital Q stands for heat, and the dot on top means the rate, and this IN means the energy which is coming in. Okay, and the energy that is flowing out is m dot times this quantity, the enthalpy plus kinetic energy and potential energy. And there may be a shaft inside which might be rotating, as in the case of a turbine, and you get some work output from the shaft. So this is the useful work. So capital W is the work, and the dot on top means it's the rate of work, and this subscript shaft means some shaft is rotating. Okay. So this does not include the flow work. The flow work is included in the enthalpy. Okay, so let us go slowly. I'll come back to this again in the afternoon session. W dot shaft is the rate at which shaft work is done. So what are the units of this? SI units?
Watts.
Watts. W shaft will be joules, and the W dot means joules per second. Similarly, Q dot in also will be watts. Q dot in will be joules, and as Q in will be joules, and Q dot will be joule per second, which is watt. Now, in many cases, you will not be intentionally adding or taking out heat. Okay, but sometimes due to temperature differences, there may be some inevitable heat transfers. So, for the sake of completeness, I've written this down. So, this is what you see in a book on thermodynamics. Okay. Now, again, this small h, the lowercase letters denote specific terms, specific quantities. So enthalpy will have units of joules, and specific enthalpy will have units of joule per kg. So I'll use, of course, here I'm not using capital H. Okay. So H is the internal energy plus PV. Enthalpy is internal energy plus PV, which you know from various courses. Okay. Now, authors of books on thermodynamics will use U for internal energy. And since this is specific internal energy, they would use small u. But lowercase u is sometimes used for the x component of fluid velocity by authors of text on fluid mechanics. So to avoid confusion, I have used E instead of U for energy. So small e is the specific internal energy. So this will be joule per kg. And small v is the specific volume, that will be meter cube per kg. So this is the reciprocal of the density. So I can write H as E plus P by rho. So this definition is valid even for a compressible fluid, but in the case of a liquid, we'll assume that this rho is a constant. Now, as I've said before, if the z-axis is vertical and points upwards, then this gravity vector I can write as minus GEZ, in which case minus G dot R is plus GZ. Okay. So this quantity minus G dot R will be simply V plus Z. Okay. So you may ask me, what is Z1? Okay. So it is the elevation of the, you can think of it this way, the center point of the inlet. The inlet section itself will not be very large. So the variation of the height above a certain horizontal datum will not be much. So you can take it to be some average value, which you can take to be the center point value. And again, we are assuming that H1 is the same at all points at section 1. And V1 is the same at all points in section 1. So the sum of enthalpy and kinetic energy and potential energy is the energy that is flowing into the control volume. This is the energy which is converted by mass into the control volume, and this is the energy added as heat. And what you hear is going out The first term on the right hand side, this group of 3 terms, is the energy that is converted out of the control volume by the mass. Okay, and this is the useful work. Of course, this H itself has a flow work. This PV is actually flow work, which you study in your fluid mechanics. So that is the work done in pushing the liquid. Now we can divide by m dot. Okay. So when you have one inlet, one outlet, I'm not calling it m1 dot and m2 dot, simply m dot. And it has the same value at both inlet and outlet. So I can write this energy balance per kg. Okay. So what I can do is I can divide the whole equation by m dot. So in the first term, I will not have any m dot. First term on the left hand side and the right hand side. And this will become q dot by m dot, and this will become w dot by m dot. Okay, so this is simple algebra. Now, this is a course where we are talking about turbines and pumps. So we are interested in this work quantity. So let me keep the work, the useful work, the sharp work on the left hand side of the equation, and let me throw this term to the other side of the equation. Then you see that the rate at which sharp work is done per unit mass per rate by dividing by m dot is the difference of the energy, that is specific energy that is flowing in, minus the specific energy that's going out, plus the heat that is being added per kg. Now this, if I want, I can group separately. There are 3 terms in this big parenthesis here and this big brackets over here. I can write it as the difference of the enthalpies, difference of the kinetic energy, and the difference of the potential energy. Now again, I can write H as E plus P upon rho. Okay, and group it separately, difference of internal energy, difference of pressure. Okay, so the sum of these two is the difference of the enthalpy. So it is almost 12 o'clock. So I'll stop here now and we'll meet again at 2 o'clock. Now, if you have any queries, I can answer. But you may have another class, so I don't want to take up your time further. Should I stop sharing? I'll quickly go through this again. Okay, first I'll start in the afternoon session from this and see what is the relevance of this to this course. By the way, if I hold a sheet of paper, is the figure visible here?